Hello everybody and welcome to day 10 of CS219 Computer Organization. Today we're going to talk about cache memory in chapter 5 of the book, and along with that I think it'll be easier to understand that if we do a review of hash tables. If you've taken 302 then you should know hash tables. I also have videos just focused on hashing in my YouTube channel under the 302 lecture videos. So you can check those out, but I will try to do a quick overview of hashing enough to better understand as to the why associative and direct access work. Because if you know hashing, it'll make a lot more sense, but if you don't, then you're basically trying to learn two things at once. So yeah, we'll go there when we get to that. So let's go ahead and start. So if you recall from last week, we were talking about different categories or features of memory. And one of the things that we were using to classify different types of memory, along with the actual physical properties of the memory and performance features and location and capacity, organization, and all of that, one of the ones that we kind of were talking about, what we went rather quickly on, was the access method. And I want to very briefly go back to that because it'll make more sense now that we're talking about caching. So when we're talking about the access method, we said that memory can be classified as these four sort of main different types of access methods, and those are sequential, direct, random, and associative. And we talked about these three, and this one we just kind of sort of said we'll talk about later, and that's why I want to revisit it, because that later is now. So just to refresh, sequential is kind of like the idea of looking at a tape, and how you search to that is you start at the beginning and read through it in order. And the access time is going to depend on the location of the data and the previous location of the data that you just looked at, because this tape has to move back and forth. And you basically have to read through in order. You can't just jump directly to a location in the tape, because it's literally a tape, so you have to wind it to the right spot. And it's just a shared read and write mechanism. So you can only be reading and writing to one location at a time in the tape. So that's the first one. Now, direct, as the name implies, allows you to jump to the vicinity of what you're looking for. So while there is still a shared read and write mechanism, individual blocks have a unique address, and that's kind of going to be like your hard drives. And so because each individual location in the disk, for example, of a hard drive has a unique address, you know where you have to go. However, there is still a physical component involved, such as the laser reader, that has to move, for example, from here to here, and that actually takes time. And because of that, if you are reading right here and then you have to go here, this is a shorter physical distance than this one, and so it's actually going to still depend on the previous block that you looked at, and the time is going to be basically jumping around, counting, waiting, and all these things. So again, the access time depends on the location of the previous item that you were looking at. However, the advantage is that you can jump directly there, whereas with the tape you have to wind it out here. You have access to the entire thing. You just have to move the reading head. Excuse me. And so those are kind of like our longer term storage solutions. But for the computer, we need something fast. And so that's what we come up with the third category, which is random. And random kind of, random access memory is RAM. And the beauty about random access memory is that there's a dedicated read and write mechanism, so they're not shared for each addressable location. So each location in your memory is going to have a specific address, and that address is going to allow you to jump directly there. And the access time is independent of the location of the previous access. So it's a constant time to access anywhere in memory. So it doesn't matter if you were looking at the bottom row in the entire RAM, and then next time you got to look at the top. It will take the same amount of time to go there per se than it would be to go to the middle or the beginning or anything, because of the way that that works. And we will talk more about RAM in the next chapter, I believe chapter 6. And so this is much better. However, of course, there are some pros and cons, and one of those can be, for example, that now we're talking about volatile memory, which that means that when you lose power, you lose basically the data in the memory, versus something like a hard drive where it's non-volatile. When you write to that magnetic surface, it pretty much remains for a longer time. I wouldn't say forever, because that is not the case, but for a much longer time, potentially outliving you. So actually, I don't know about outliving you, I don't know about that. Some people say the hard drives will last a long time, but not sure about the limits, because we haven't had them long enough to really kind of analyze and do statistics on how long they've lasted. So anyways, that brings us to associative, which is what I want to talk about today. So what is the associative access method? And so the thing about that is that data is located by a comparison with the contents of a portion of the data itself. So basically, you have to think at sort of the logic gate level, because what associative memory can be also referred to is as content addressable memory, which is CAM. And that's actually just another nickname for associative storage. And it's built with static RAM cells, and it is much more expensive in terms of actual cost, and holds less data than regular SRAM chips. And it's also larger physically, about 60%. And how it works is that when a bit string is applied, the CAM searches the entire memory in parallel. So this is very tricky to draw. And there are some figures in the book, but if you don't know what to look for, then they just seem very confusing. So let's think about the data. So let's think about an easy problem here. We are looking for some data that is stored in a data structure. So for example, let's think about binary. So let's say we have a little array, and hopefully you can't hear the dog crying. Ignore that, she's okay. I locked her so she didn't come in the middle of the recording. So yeah, okay. So let's say that we had the following data, okay? The following data structure here, just a little array with 4 items, okay? And these 4 items are gonna hold a bunch of binary values. And even though I made it pretty wide, I don't think I'm gonna put that much into it. So maybe you put 1, in fact, actually, you know what? I'm gonna space it out better. So let's actually put these lines like that. Yeah, this will look much nicer, okay? So let's go ahead and then maybe do this. Okay? So suppose that I was looking for the following, sequence of bits here. Bunch of zeros, okay? You can already see that it's not found, right? But how can I look for it? Well, if we think about our sequential way of accessing things, a linear search per se, one of the things that we can do is we can just kind of look at the first bit here, and if the first bit matches with the first one, then we look at the second bit, of the first row. So first we're just dealing with the first row, so let me highlight it. So we're just looking at this and we're comparing it with what we're looking for, which is this. So the first thing we do is we compare the first bit of each of those. So we're comparing this and this. Because they match, then there's a possibility that we have found a real match. So we want to check the second bit. So the second bit is this second 0 here, which is compared with a 1, and now that doesn't match. So at that point you can discard and say that this does not match this, right? So then you move on to the next row, and then you start over again. So 2 for loops essentially if you're coding something like this. So then you're comparing the 1 here with the 0, and you see that there's no match. So there's no point in checking the rest of it. At that point, you can discard this as a possibility. Then you move on to the next one. Again, you discard it with the first possibility, then you move on to this one, and you discard it with the second one. Now, suppose that we did have another row here that had all zeros. Well, the way you would confirm that it's a match is you would look at the first 0 and you would see that there's a match. And then you would look at the second bit per se, and you would compare it to the second bit of this one, and you'd see that there's a match. Then you move to the third one, compare that, see that there's a match, move to that, compare that, see there's a match. Now, how many comparisons do we have to do? Let's go ahead and count them by highlighting them with this pink. So we got to compare that. We didn't have to compare the second one there because that first one basically said that was not a match. Same here, we just have to compare 1. Here we did have to compare 2, and then I suppose in the match we technically had to compare all 4. So we had to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Potentially we had to do 10 comparisons to be able to say with confidence that, well, if we have the bottom row that we found it and it's in the bottom row, or if we didn't have that bottom row and we couldn't find it, then we would have to still search for that. So that would mean we'd have to do 2, 4, 6 comparisons before we could say it's not found, right? So that, if you took 302 and your time complexity is going to take O of n time, n being the number of, potentially the number of rows here. Actually, linear search takes n time, but we are searching each individual thing. So in the worst case scenario, it could be something like all of them contain the following, 0, 0, 0, 1. They all contain that. It's like duplicates. That will be the worst case scenario, because in that scenario, we have to compare pretty much just about every single bit before we can discard it. Because we have to look at the first 3 because they're a match, but then when we look at the 4th one, then we say it's not a match. Well, we already kind of wasted time looking at it. So in this scenario, for potentially 4 rows, we had to look at 4 times 4 number of bits, so that's 16 bits. And since the original one is 4, then that's technically 4 squared. So I'd say that's an n squared search because we're matching each one. So I know it looks like just an n search, like linear search, but because we have to within each row, we have to compare each individual bit. In reality, this is more of like an n squared scenario. Although actually no, the correct string, the correct time complexity would be n times m. N is the number of rows, and m is the width of the string. Yes, that's actually correct. Apologies. I guess it's been like 3 months since we did 302. But yeah, so it would be n times m. Why would not n squared? Because, well, it just happened to be that here we have 4 rows and 4 bits. But suppose that the word that we're searching for, this happens to have 16 bits. So each of these are going to be 16 bits potentially, which means that as we were searching through this, we have to potentially check 16 bits per line. So that would be 16 times 4. So in that case, it would be potentially the worst case scenario would be this. And so that would be represented as 4 times 16. So again, it's not just related on the n, it's related on the length of the string, which I called width, okay? So yes, and the real time complexity is n times m, which again is going to depend on that. So anyways, what I'm getting through this is that this is a rather expensive process to do if you're dealing with something that you're trying to make fast, right, with cache. And in general with memory. So this is not the best way to do this. The other way, if you took 302, that you learn to search faster is with some complicated data structures such as binary search trees and other things. I don't want to jump into that, but what we can think about in the level that you guys probably know if you haven't taken 302, but you took 134 and 202 is how to do binary search. And binary search involves first you have to take this list here and you would want to sort it out. And when you sort it out, you can use the binary search algorithm, which would potentially take log n time. Now, in reality, that is more like log n times m time, okay? That's what you're really probably looking at here. Actually, this might be log n times log m. Let me think about that for a second. Nope, I think you would actually be doing log n times m still. But either way, even though that's fast, it's still not fast enough for our purposes. And also, it involves a really complicated data structure that would be very expensive to kind of make at this level of cache. You know, we're trying to keep things simple and small with the least number of steps involved because each step takes time. So another way that you could search things is with hashes. And so let's talk a little bit about hashes, and then let's talk about how you could actually implement something like a hash at the hardware level as well. Because here's the thing. Think about just an array. You know, you got yourself an array, and it's got indices. And we know that if we say, give me, let's say this array is called AR. So we can say, give us AR of 4. That's the 5th index, again, because arrays start counting from 0. And then we know that that's instant. You know, that's a constant time to be able to retrieve that. It's very, very fast to retrieve that, right? We like that the ability to quickly get there. Now, if we're searching, is it possible to achieve this sort of immediate ability? And the reality of things is that yes, you can do it. You can do it with hashing, and then you can also use content addressable memory. Now, let's actually talk about contralateral memory first. Actually, yeah, before I show you hashing, because that will take a while. So, suppose again, you have to really think about the hardware level here, because this is all we're storing, and this is zeros and ones. If you think about at the hardware level, we could use the AND gate. We could wire each of these individually, each of the squares, to an AND gate. And the input of the AND gate would be what we're searching for. So let me go ahead and actually explode this picture so that I have space. So yeah, let me go ahead and do that. That will make things a little bit easier. So we're just going to take the same data, but we're just kind of explode it so I have space to sort of physically wire this. So we're going to the hardware level. We're going to the CPE people for this. So let me just copy the data. We got 1 1 1 0 0 1 0 0. Okay, and so and yeah, we can throw in the 0 0 in there as well because we might want to see a match. Okay, that's acting weird. So let me just copy this again and then line that up. And I hope that everything is recording just fine. We have audio, right? How sad would it be to record this whole thing and have no audio? No, we do have audio. Cool. Okay. So, great. Okay. And again, what we're looking for is 0 0 0 0. Okay. However, let's go ahead and actually put them vertically so it's easier to do the schematic here that I'm trying to do. Okay. So we're just going to put this vertically. This is what we're searching for, okay? So what I'm going to do is I'm going to show you how I can search this in basically, you could say instantly. However long it takes you to do a single comparison. So in the old method, however long it took you just to compare the first row's first character, which happens to be this 0, with this 0, however long it took you to do that one comparison, I'm going to basically show you how you can just check the entire table in the same amount of time. Okay? Just that quickly. How are we going to do that? Well, it's impossible to do sequentially. However, we can use parallel for that. And by parallel, I'm saying that we're going to check everything at the same time. And that's how we're going to achieve things to be able to take me one time. So how am I going to do that? Well, I'm going to just use an AND gate. I believe they called it a comparator or comparator or something. But essentially, if you guys remember your CPE, which I didn't, so the other day, if you guys are watching the videos, you saw me just randomly have a flashback and remember that this is an OR gate with the little curve thing, and the sort of squarish one is the AND gate, And so we can take advantage of the fact that the AND gate returns 1 only when both the right and the left are 1. With the OR gate, it can be this, or even this. They will all return 1, right? But since a match is when things match, you know, when we have this and this be equal, we can sort of take advantage of that to be able to see if things are a match, okay? We can also use a NAND gate as well. Let me check that one actually before I go and say something wrong here. NAND gate truth table. No, the NAND is basically the opposite of the AND gate. So which one do we want to use here? Maybe the XOR. Maybe that one will work. Let me see what the XOR table gives you. Here we go. So I think the one that we could take advantage of is the Xnor. Yeah, so the Xnor. The Xnor table. Or sorry, the Xnor truth table. So the Xnor truth table, that one has the following logic gate. If you give it, if you have like A and B, and you do your Xnor, then 0, 0 will give you a 1. 0, 1 will give you a 0, 1, 0 will give you a 0, and then 1, 1 will give you a 1, okay? Now, the normal AND will basically just give you 0, 0, 0, 1 here, but, and even though in the book, that's probably what they're using, I'm gonna use the Xnor to show you what I think might be easier for you to understand. Let me just see if the book has, well, the book has a comparator as whatever, but let's just do that. Let's just use the Xnor. And what is the symbol for the Xnor? Actually, let's see what the Google says for that one. So that looks like this according to Google. Let's see if I can draw this right. It's kind of looks like the OR, like that, and then it's kind of curved like this, but then there's a second line here. Oh, that failed. Let me try that again. Like that, and then we have this and this. Okay, so this is our A and our B, and there's our output. Okay, so why do we want to use this one? And by the way, how do you build this one? How do you build an Xnor? You can build it with two AND. I believe you can make it with two ANDs, and then with an XOR, or sorry, with an OR. Is it OR or XOR? Well, let's try it with this. But then I think one of them you gotta flip, don't you? Yeah, you gotta flip them both. So you gotta put a not in front of each of these. So yeah, because what's gonna happen is the normal AND gate only will give us a 1 if the 1s match, right? But now we want to make sure that we get a 1 with the 0s match. So we get 2 zeros fed into this thing. So here, let me make some space. And I know I'm going into the CPE stuff, but that's really because I want you to understand why this works. It's not black magic. So, and we must prove our superiority to the CP people by showing them we know this stuff, right? So, as CS people. So, we have our 2 AND gates, and then we have our initial inputs, okay? So we're gonna wire this like this, and then we're gonna also wire that here, and then we're gonna wire that there, and then wire that there, okay? So, yeah, so this one is going to both top, and then this is going to the both of the bottom AND. So here, I'll call this one A and B. So this is A, and this is B, and this is B, okay? And so last thing that I need here is that before I get them here to the entrance here, I'm going to, because otherwise it would be pointless to have 2 of them together. I'm going to go ahead and put a NOT gate here. So the NOT Again, if you feed it a 0, it becomes a 1. If you feed it a 1, it becomes a 0. Okay. So what's going to end up happening is the bottom AND gate here is going to take, if it takes a 0, 0, a 0, 1, or a 1, 0, any of those is basically going to have a return 0 here. Okay. However, if it takes 2 1s, then it's going to return a 1. Okay. So that takes care of the situation where 1 and 1 are matched. But we also want it to match when they're both 0, 0. And the reason why we want it to match is because we're going to compare what we're looking for with this right here, right? We want to compare that. And the two scenarios are that we're looking for a 0. If we have a 0 here, we want a 0 to be there. If we have a 1 here, then we want a 1 to be here as well, right? We want them to match. But if we have a 0 in the search string, so let's call this the search, and let's call this the cache, or the array. Just call it the array. No, forget about the word cache for now. Search and array. You know, if the search and the array match, so if they're both 0s or they're both 1s, we want it to succeed and say a match, which we return a 1. However, if this one is a 1 and this one's a 0, or vice versa, then we don't want it to match and we want it to return 0, right? So that's exactly what the Xnor is giving us, right? If we have A and B are both 0 or 1s, that means that they're matching, right? Because 0s match or 1s match. But if we have these that don't match, then we don't want it to return true. Okay? And so that's what we're trying to achieve. And so the way we achieve that is on the bottom, we take care of the scenario where they're both 1s. But now we got to take care of the scenario when they're both 0s and return a 1. We can't just use an OR gate because an OR gate will give us 0, 1, and 1, 0, which are not what matches should be. So all we do is we just flip the inputs. So if we get a 0, 0, by passing them through the NOT gate, those 0s are going to become 1s. And that's okay, because if we fed 0, 1, then that would become 1, 0, which is still not a match in an AND gate, or vice versa. If we see 1, 0, it becomes 0, 1. Again, not a match, right? So as long as we are flipping both of the inputs, then we're safe. And so now, this technically we're feeding 2 1s and we get a 1 back, but in reality, from the original input, we're really feeding it to 0s. And then, of course, we put an OR gate here because if either of these return true, it means that we have either 0, 0 or 1, 1. So if either of this is 1, you know, with an OR gate, as long as one of the two are true, then this becomes true. So basically, that's how you implement this Xnor truth table based with just 3 gates, 2 ANDs and 1 OR. Well, actually, no, like 5 gates. You have 2 NOTs, the little triangles here, and then you have the 2 AND gates and then 1 OR. I don't think you can do it with less gates. Maybe you can. That's beyond the scope of this course anyway. So now you know how we came up with this magical Xnor gate. Okay, so just a bunch of CPE stuff. Okay, so basically, you know, I'm gonna draw this again and make it really tiny so I can put a bunch of them. But let's try that again. It's really hard to draw stuff nicely here. Okay, close enough. There we go. Okay, so that's going to be my template. I'm just going to copy and paste that up a billion different times. So I'm just going to basically hook that up here. Probably going to make it much smaller. Yeah, I like that. And then I'm not going to do it for every single one of them, because that's going to take me a long, long time. But I'll do it for at least a little bit. Okay, so here we got one of these gates. And what we're going to do is we're going to hook it up with the first digit here to that input, and then let's go ahead and we're gonna need more space here, guys. Hold on a second. Okay, and then let's move on with this. Okay, didn't lose anything when I slid it down, and then slide this down. Turns out that it might actually be easier to put this like that. Okay, so I have enough space to be able to do this. Okay, so this is what we're looking for. So now we're gonna space it out pretty big here so that we can actually fit this up. Okay, so now that wire, and I guess I can use different colors for the wires. So I'll start switching colors, yeah. So this little wire is gonna go there, okay? And then for the second one, we're gonna do the same thing. We're going to put another one of those. Actually, doesn't matter which of the two you put into each one, actually, at this point. So if the top wire here goes to the search or the array, it doesn't matter, as long as one goes to each thing. But I guess I'll be consistent with my color coding. So we're going to have all these go here, like that. And then, let's switch colors here. We're going to make this orange, actually. So this is going to go to the second one here. This is going to go here. This is going to go here. And then I guess we needed one more. So, yeah. Paste, please. Paste. Okay, and then let's put like a couple more. Just pasting them. We can move them around later. And then we can wire that right here. Oh, we have a little short circuit there. Those wires touch. You know, why am I suffering when I can zoom in? Sorry, guys. And then let's wire that red cable here. Oh, I don't want to. Ah, not there, not there. It's okay. We'll just say that the wires isn't touching, right? You know, they're not copper wires. They have a little bit of, well, actually, at this point, this is all at the semiconductor level. But imagine now we're doing breadboard level. Okay, so we got a little thing that can compare against 5 of these. Okay, and now what do we do with the output? Well, we need to have we have to have a little. Well, this gets even more nasty with the CPE stuff, I suppose. But now we want to make sure that if all of these return true, then we're good to go. So put all of these wires, again, these wires aren't touching, they're just crossing on top. These are all the outputs, right? So we are going to accept whichever one of these returns a 1. So if any of these return a 1, then we'll accept it, okay? However, now we need to do the same thing that we just did for the first bit for the second one. So I'm just going to do it for the second one. Maybe I'll do it for the third one, just to have a little more space, okay? But you would have to do it for all 4 of these. So now let's do it for the third one. So let's pick a different color. So now we're checking the third bit, okay? So that would go with this one. This would go with this one. This one. Sorry for the zigzags, guys. There. And then let's hook up the other end to the third bit here. So this goes, I should just make this the logo for the video, because people will see it and be like, what the heck just went down here? And we're not even yet to caching. Okay, and then are we missing one, or did we hook them all up? We're missing one more here. This one. Okay, so they're all basically hooked up there. Okay, and so now what we need to do is we need to hook up the output. So let's get the outputs again. What color haven't we used here? Pink. So let's bring all the cables up here as well. So this is all the 5 outputs that we have from the Xnor table. I guess we can bring that one through here. Okay, so here we go. So suppose that we were just comparing those 2 bits. How do we know which one's a match? Well, they all have to be 1. If they're all 1, then we have a match. If they're not all 1, then we don't have a match, right? Because the Xnor is going to return to us a 1 if that specific bit matches what we're looking for. And so if, you know, the only things that we were comparing were the first and third bit, then we would have to see which of these lines both are returning 1s. So how do we do that from a transistor level here? Well, they can just be an AND, another AND, just one single AND in here. So what we can do, well, not one single AND, but a bunch of them together, I suppose. So this is just going to be an AND gate. And what you end up doing here is you end up wiring, oh, no, this color. I think it's this color, yeah. Let's say we're going to hook up, oh shoot, I don't know which is which. Let's see which one's the first one. So okay, so this is the first one. So that was from the first column here. So we're going to hook that up to here. And then let's see where the other one is. So that goes down here, that goes, so it's this one. Okay. Okay, so that one goes to there. Okay, why is it that one? Because we want to make sure we connect the first and third bit of the same row. And that's this one. If you want me to follow that here, I'll follow with the highlighter and then I'll erase it. So ultimately, we are seeing this goes here. And then it goes, oh man, they do cross a little bit here. But you can kind of see that it goes here, okay? So that matches with that one. And then we can see here that that matches with that one, which matches with that one, okay? So we are comparing with an AND gate here, the first and the third bit of the same row. And I hope that it's not obvious, but clear as to why, if this returns a 1 and this is an AND gate, why that means that this is a match. Because that means that if this returned a 1 and this returned a 1 is because it was either 0-0 match or 1-1 match, either one. And so if both of them return 1, it means that in both scenarios there was a match. So that means that both of the bits match. So that means that if that's what we're looking for, then we're in business. That means that we did have an actual match. Now there's more than 2 bits here. There's 4 bits. So what would end up happening is the other 2 bits would have another AND gate coming in, you know, like this. And then they would also come out. So then you would have to have an AND gate between these two. And now finally, this will be the final output. If this is a 1, then that means that you have found the match. You have actually found the match, if that's a 1. If it's not a 1, it means that, say this is a 0. So for example, in this case, 1 and 3 do match, but actually 2 and 4 don't match. So that it's going to actually be that both of these are 0. So this is a 0. So that's why this will return a 0. So while this one will return a 1 because both spots 1 and 3 are 0s, but what we're looking for is all 0s, then this is the 1. Now here's the thing. Yes, I said constant time, but constant time in the sense that once you add all these, the time it takes to go through all these logic gates and get to the final result, which is not a lot. Let's see. In the worst case scenario, including the NOT, we have 1, 2, 3 to get here. So that's 3 to do the XNOR. And then from there, we have another AND 4, and then the final AND 5. So we have potentially 5 logic gates to go through. Now, I don't know from the electrical engineering level if they can do this with one single transistor. I don't know that, you know. But even if they didn't, because I do know that they can do an AND and an OR and a NOT as a single transistor. I'm pretty sure that they can do a couple of other ones. But assuming that they can't do something like this in one, they can probably do at least the XNOR in one transistor. But if they can't, that's okay. Even if they can't, it's going to take us the worst case scenario of 5. But here's the thing. In those 5 logic gates, you know, are going to tell us if this is a match. And that can happen at the same time as this one, right? Because the electricity can flow through all of these at the same time in parallel. So they're all actually going to finish at the same time. And what you're going to do is you're going to look at the output. So you can have sort of an output bit, which is what this is for each of these. So it's going to be 1, 2, 3, 4. I think we have 5 of these actually. So 5. And so, you know, this will be a 0, 0, 0, 0, 1 because that one is a match because it has all zeros at the bottom. So then all you got to do is you got to look at this. And of course, that's even more logic gates. But, you know, you look at them, you can, again, see which one's 1. And then you have succeeded in finding a match. And so that is basically how content addressable memory works. As you can see, even for such a small example with 4 bits and 5 rows, that's a lot of logic that you have to throw in there. It's a lot of logic, okay? And so that can be very expensive to make. But, and it also takes a lot more space. As I said, I think it's 60% more space. So it's not the best, however, you can do it extremely fast because, again, it's all searching in parallel. And so you can search the entire array. So imagine you can search an entire array of whatever size pretty much in the time it takes you to search one single bit. Okay? So, of course, you know, you got to merge the results. So it's a little bit misleading. But the point is that you can do it extremely fast. It's much, much faster than linear search or binary search or any of that. Okay? So hopefully this kind of makes sense with the content addressable memory. And so that's basically how associative, which was the original thing, was how the associative access method works. And as you can see, access time is yet again independent of location of the previous access. And basically, as I said, the data is located by a comparison with the contents of a portion of the store. Now, you don't have to completely search the entire, all 4 bits. You know, you could look for 3 bits instead of 4, but then you risk a collision, right? So, you know, that's sort of the if you want to make sure you actually have an exact match, then you have to search it through all of them, and that's more logic. But it's very, very fast. Basically, this process only takes 1 clock cycle potentially if done right, and so very powerful. Okay, it can search the entire memory in parallel, and so yes, that is content addressable memory. And so now that we have explained that 4th access method, the reason why is because this is how caching is going to work to search through your caches. Okay, so let's talk about caching. So I know that we talked about it last week, but let's make sure that we kind of understand that. And I know Sam also talked about it in the lecture on Thursday. And so, and I think we also talked about it on Wednesday. So you have your CPU, and then inside is actually, let's make a bigger picture of that. You have your processing unit, and inside you might have a core, right? So let's say this is core 0. That core has cache, potentially L1 and L2 cache, which is bigger than L1. And then if this is a multi-core machine, you might have a core 1 here, which has its own L1 and L2. And then they both might share an outside of the processor, or it could actually be in here, I don't know, wherever, an L3 cache that's shared, okay? But it really depends. It could be outside. I'm not sure what the architecture is lately. But the point is that this one is shared between cores, which causes a lot of problems. It causes problems, but they're not necessarily mean that it makes this a bad idea. It's still a really good idea, but it does mean that you have to be more careful about things, because one of the usages of a single, if you have a single system that just has, a processor and just one level of cache, just an L1 cache, and then main memory. The idea of using cache is that the time it takes for the CPU to request information from the memory and then from memory to actually send it back is a very slow time in terms of computer speed, processor speed. You lose a lot of cycles just waiting for the data. So what you do is you create faster memory that is physically closer, so you can communicate faster as well with the CPU. However, you're limited by cost and also space and how much of this cache you can have here. And so you're going to put the best memory possible there, the fastest memory, the one that you probably can't afford to pay for having an entire RAM of, because again, that is the cost benefit that we were talking about. The more space you have, the cheaper the bit is. However, the faster you want to access it, the more expensive it is. So it's a give and take between having a lot of space, having fast memory, and what was the third one? Transfer rate as well. It's the pros are you want to have a lot of memory, which lowers the price of memory, or so the more space, the more memory you have, so the bigger like a hard drive you buy, the cheaper each bit is. That's one good thing. However, the faster the memory, the more expensive it is. And also, I think it's the bigger the memory, the slower the access time is. I believe that's the case, but let me triple check now, because I just realized I can't remember that property. So let me just make sure that I remember that. Here we go. So faster access time is greater cost per bit. Greater capacity is smaller cost per bit. So the bigger the hard drive, the cheaper. And then greater capacity, slower access time. So yeah, so it is. So if you have a bigger memory, it's slower. So we all want a lot of space and have very fast space, but we can't do that. We either have a lot of space or we have a fast memory. And so, we have to give and take. And so one of the ways that we can sort of have our cake by having both situations is by having a little bit of fast memory and a lot of less fast memory, slower memory. And so that's what we have the main memory with cache. Okay, and so now What we're going to do is, if we need to be able to copy certain pieces of information into the cache so that that can be accessible by the CPU. But then we have to ask the question, what do we copy? Because we can't fit the entire main memory there, right? We have to copy pieces of it. And so which pieces do we copy and when do we copy them and so on. And so we talked about the principle of locality in terms of spatial and temporal locality. Spatial locality means that when you're using information, odds are that the information around that information is going to be useful to have because it might be accessed pretty soon. So, if we're working with an array and we're dealing with this element in the array, there's a very high chance that we're going to be looking at the stuff down here or maybe even the stuff above it in the future because it's an array. And if we're doing sorting, then yeah, we probably are, right? Similarly with instructions, it's very likely that the instruction beneath the one that we're working with is going to be the next one that we look at. However, there's still also a very high chance that the instructions before us will be looked at again. Why would that be the case? Well, suppose that this is a little loop in here. So this whole code is a loop and this is where we're at. So when the loop finishes, then we're going to go back up to the top and it's going to go again. So that's going to be your spatial locality. There's also temporal locality, which is basically the idea, think of stock markets like previous performance does not indicate a future performance, but yet again, all our machine learning is based on previous performance will indicate future performance. And that's kind of what we're going for here, saying that if we just ran an instruction here, and then next we're running instruction here, then there's a high chance that the instruction that we just ran might be run again in the future. Or if we were working with data, if there is an array or a specific variable that we just accessed, there's a high chance that we're going to look that back in the future. And when we graph those properties, you see that you have these sort of double humps when it comes to spatial locality because, you're using data here and it's all the data around it is very likely, and then the spatial locality goes down and then starts up again because you're using another cluster of data. Temporal locality typically looks more like this. You're using stuff right before, and then it kind of goes down as the program finishes. So we can take advantage of that with the cache by basically saying, okay, if we're loading a specific address in memory, let's load stuff around it because we might use it in the future. And also, if we just had something in the cache, let's leave it in there. If something just got requested in the cache, let's leave it in there as long as we can because it might be used in the future. Obviously, if we get newer requests and we need space, we can replace it. But we can replace the oldest thing that we haven't used, right? So that we're always throwing away the oldest thing that we've been using. And that's one of the ways that we can achieve that. So again, hopefully this is a lot of review from last week. What now we really want to talk about is how things are stored in the cache. And for that, I'm going to switch gears and first talk to you about hashing, okay? Because then it'll make more sense once I talk about the different ways of storing information inside of your cache, which is going to be the different mapping methods they use. So hashing, and again, you can watch my videos on hashing to understand it. Otherwise, you will learn about hash tables and hashing in 302. Okay, so again, going back from the idea in the beginning that one of the ways to search information is to just do linear search. It's not very efficient, but it gets the job done in n time, or potentially n times n if you're thinking about string matching. The other way is you can of course do something like a tree or linear or a binary search, which basically gives you have to pre-process the data in some form so that then you can search through it faster by basically, binary search, for those of you that don't know what it is, which I hope you all know, is the way you look in like a dictionary. You open the dictionary in the half, and maybe that's from A to K. And then if you're looking for the letter S, then you're going to look in this side of the dictionary. So you open it in the half again, and here you're maybe at U. So then that means that S is going to be on this part of the dictionary. So then you go ahead and open that in half again. And so maybe now you are at R. Okay? So that means that it's over here because it's RSTU, right? So in here, then you find S, and then you can move on to looking at the second character of the word you're looking for, and so on. This is a lot faster than trying to look through a dictionary by searching from page 1 all the way to the last page, right? You're never going to do something like that. That would be insane. And so while we might do perfect binary search in a dictionary, we kind of get pretty much do the basics of that, at least until we get to like the last few pages. And then you probably go page by page at that point. Whereas the computer can do it perfectly and really achieve log-n time for searching, log-n comparisons, you can think of that. Okay? So, there is another way, well, here's the thing. To be able to use this method, it requires a dictionary to be sorted, right? So when you're looking at a dictionary, all words are alphabetically sorted. If they were not, if they were just random, if somebody just put all the words in any order they wanted, it'd be practically impossible for us to find a word because we would have to search every single page, okay? So sorting of the dictionary, so basically sorting things alphabetically takes time, okay? So it's not something that we just get a free lunch. So it's useful, it's faster to search strings, but you have to prepare the data. And with cache, think about it. It's already enough that we're copying from main memory to cache data, but if we have to consider sorting the data before we can actually make it accessible quickly, that's going to take time and that's slowing things down. And so one of the solutions that we can do is, well, as you already saw, it's addressable memory. But before that, let's think about the concept of hashing, okay? So the concept of hashing is, let's think about phone books for that, in fact. Yeah, direct access. Let's talk about direct access, which can also be direct mapping, which is going to be one of the ways that the caches work. So, suppose that you wanted to keep a phone book, and in the phone book, you're gonna have phone numbers, right? So there might be something like 702-895-111. Somebody, and let's say this is the phone book of Mr. Smith, okay? And then you might have another phone book that is 702-895. Hopefully these are not real phone numbers. 9999. And this is Miss Jane, I guess. That's not really her last name. So Miss Jones. I always get mixed up which is between MRS and MS. I don't know. But anyways. And maybe somebody else has a phone book of like that. Okay, and this is Timmy. Timmy doesn't go by his last name. So, if you're keeping a dictionary, one of the ways that you could store it is you could just kind of make an array of size 3 and just put it like that, and then you're searching through things, right? But then again, you got to do your linear search, or if you sort things out, then you can do faster searches, but that takes time. One way that you could do this, and this is sort of a suppose, is imagine that you just make an array of size 1 billion. Okay? 1 billion spots. Why a size array 1 billion? Because now, if you make an array of size 1 billion, then, you know, the indices are going to go from 0 to 999. Actually, one more 0. Apologies. We do want one more 0 here. So 10 billion, actually. Now, why we want to do that? Because then the array goes from index 0 to index 9,999,999,999, which happens to be all possible range of phone numbers that anybody could have, right? In fact, actually, I would say that nobody can really have phone number 0 or anything with less digits, actually. So maybe the reality of things is that the range of phone numbers actually kind of goes from, assuming that this is a valid area code, the range of phone numbers would be really from that and up, right? Because you need to have at least a 1 here. But either way, we can't really easily declare it like that unless we do a little math function. So we're still, we're going to make our life easy and we're just going to declare from range 0. And we're just going to, either way, there's going to be a lot of empty spots in this array because really we only have 3 phone numbers. But we have an array that's pretty big, 10 billion spots. And if this array is storing people's names, first and last name, and or just a big string, you know. Suppose that this string is going to take us to store, well, each car, you know, you could think of each car as 2 bytes, or actually 1 byte. But let's say that they're each stored as 4 bytes because it's a very inefficient system. And if that is the case, and say we are allowing maybe a maximum of 100 characters in the name, that would be 400 bytes. And so we got to take 400 bytes and multiply it times 10 billion. That is going to give us the equivalent of 4000 billion. So that's 4 trillion bytes, which I believe would be 4 terabytes, because let's see, megabytes is millions, gigabytes is billions, and trillion. Yeah, so 4 terabytes. So it'll be a 4 terabyte array, up to potentially. Well, you know, because the string is variable, so the memory gets allocated at the time. But let's just say that it's allocated ahead of time. It's just a big, massive array of cars, and they're just set all to blank unless you're putting stuff in it. So it's a 4 terabyte array. Pretty achievable. I mean, obviously we can't keep this in main memory unless we have a lot of main memory. But we could probably keep this in a little hard drive, you know. And yeah, so there you go. You have a little array. Now, what's the advantage of this array? The advantage of this array is that if I want to access somebody's phone number, I can just put the index. So if I want to find out whose phone number is 702-895-999, all I have to do is basically, you know, suppose that the array is called PH or just phone book, you know, then all I have to do is say phone book and then pass in 0702-895-9999, you know, and then if I overload the cout operator, you know, I can just cout phone book, and basically whatever this returns is going to give me the name. And if I don't want to overload it, I can get a print function so that I can do something like .print, you know, this is C++, and then that'll print out the name of the person, right? And that is an instant. That's going to be an instant time. There is no need for searching, because you know that the phone number is the index. And so because you know where the index is stored, it's just a mere pointer arithmetic situation to get there. You're just adding basically 400 times that number, and you go down that number of spots in the memory and get that specific area of the array. So that's a constant time thing. And of course, if no phone number exists, then we can go ahead and instead of just have a blank name, and that represents the phone is not associated with anybody, right? And so using this method, we can basically have data, a phone book of every single person on the US, because I'm guessing, you know, this was US area codes, and we can basically access that in constant time, very, very fast. There is no searching involved, because the phone itself is the way to access it. Now, there are limitations to this system. Basically, if we want to search for what the phone number of a person is, that we cannot do, because while we can use the index to find out who owns a phone number, we can't ask, like, what is Timmy's phone number? That we can't do. We would have to linearly search through the entire thing to find out where Timmy's phone number is, right? But if, you know, so that's going to be the limitation of this system, is that while we can search for people's names given their phone numbers, we can't do the opposite. If we wanted to do the opposite, then what we could do is we could make some sort of math conversion to make Timmy into a numerical value, but then we have to make sure that no two people have the same name, which it's unlikely, so that wouldn't really work. So this is only working for the scenario where we're retrieving information based on a phone number, okay? And as you can see, that phone number is going to be an address, kind of like how we're going to be doing with cache. Now, what are the disadvantages of this method? The disadvantage, I hope it's clear, that we have 3 phone numbers, but we have 4 terabyte array for 3 phone numbers. You can see that it's just a big waste of space, potentially, for just 3 numbers. So when you get to 302, you get to talk about the whole space versus time, you know. Sometimes you can achieve faster results, but they take more space. Sometimes space is the limiting factor, so you'd rather do things slower, but take less space. Here's a good example of that. If we just kept this in a little array that was just the 3 items, all we got to do is search to that array, and we would have the same amount of data and kept in basically you know, on a couple of bytes instead of 4 terabytes. And so that is a little bit slower though, technically. You have to search potentially to 3 records before you can confirm if somebody is there or not, you know, if a phone number is valid or not. Whereas here you can find that immediately, but at what cost, right? And so I see as people, you know, yes, pros and cons, but can we sort of reach a middle ground? And so that's kind of where hashing is going to come in. Because let's kind of look at the numbers here for a minute and see what they share and what they don't share. We can see that the numbers have a different area code. The 2 of them have the same area code and one of them has a different one. And they share the same last 4 digits here as, you know, those 2. However, you know, I could go ahead and say that the combination of the digits, hold on a second. The combination of the digits, I think my dog was able to escape his encasing. So let me, hold on a second. I'll be right back, guys. Maybe we'll do a part 2 video, so just click to continue part 2, because my dog has escaped his imprisonment.